In this video, we are going to introduce more formally the concept of an indefinite integral, which is similar to the definite integrals that we've been looking at in the last couple of sections, without the bounds where we start and stop our integration. So typically the a and the b at the top and bottom of the little integral symbol. So essentially, we're going to stop calling we're going to stop using the word antiderivative and instead start calling them indefinite integrals. So instead of antiderivative and that terminology, we will use indefinite integral, or more often than not, just integral. And it'll be clear from the context whether it's indefinite or definite. So basically, if we've got the integral of f of x dx, and notice I did not put any bounds here or here, there's nothing in those two places, that's just going to be equal to some capital F of x. All this means, so this is the notation that we'll use, and it just means that if I were to take the derivative of that capital F, I would get the lowercase f. So essentially the capital F is the antiderivative of the lowercase f, and we're going to stop calling it an antiderivative and just call it the integral. So for example, if I want the integral of x squared plus 1 dx, all that is 1/3 x cubed, that's the antiderivative of this x squared term, plus x, which is the antiderivative of the 1. And then because there are no bounds, we have to remember our plus c from our antiderivative. And it's because if I were to take d dx of 1/3 x cubed plus x plus c, I would get back the x squared plus 1 that we started with. So this is basically this line written with an actual example in place. So if you want to look in the book, I believe it is on page 403 in our book. I know that's the physical one. I'm not sure exactly where it is. It'll be in this section on the ebook, and it gives a big list of some common indefinite integrals that show up. And it also gives us a few of the basic rules, and some of the basic rules. So it might be good to take a look at that if you've got the time, but essentially, for the most part, they're ones where we know sort of the pairing of a function and its derivative, and if you think of the derivative, then the original function is the integral of that derivative. So basically just a pairing of function, here's a function and its derivative, or if you read the table in the other direction, here's a function and its integral. So that's kind of the idea. So, let me see actually if I can bring that up here. Let me just pause this for a moment and find that table. Okay, so here is that table. This is table 1 in section 5.4. You can see that it's got some sort of general rules about integrating a constant times a function, and how we deal with something like that. Oops, let's close that. So we've got a constant times a function, we've got the sum of two functions, we've got polynomial terms, x to the n, how to integrate a constant, integrating 1 over x, b to the x, some trig functions, exponentials, a whole bunch of stuff. Basically everything we've done this semester shows up somewhere on this list. So again, this is table 1. from section 5.4. So I pulled this straight out of the ebook. I'll leave it in here in case you would rather have it in this location. Okay, so there's the list. You can use that. For example, if I want to compute the integral of the following, if I want the integral of 4x to the 6th minus 3 secant squared of x dx. Again, let me toss some parentheses so it's clear we're integrating that whole thing. We can use some of these rules and pull the constants out. So this is going to be the same as 4 times the integral of x to the 6th dx minus 3 times the integral of secant squared of x dx. So I've utilized, there we go. I've utilized this rule to pull the constants out. I've utilized this rule to take the integral of a sum into the sum of two separate integrals. And now I can look through, I have my general power rule, x to the n. Well, that's given right here. And I've got secant squared, which happens to be the, if you integrate that, you happen to get tangent. So in this particular case, looking at what we've got here, I'm going to get 4. The integral of that x to the 6th is basically 1/7 x to the 7th. Over here I have this minus 3. The integral of that secant squared is tangent of x. And I've got my plus c. And if we just clean it up, you get 4/7 x to the 7th minus 3 tangent of x plus c. That is the general integral, indefinite integral of what we're looking at over there. And so this is going to be one of the important, useful things that we're going to need to keep in mind. And you may have some things that are maybe a little bit trickier. They don't show up directly in the table. Something like this. Maybe I've got the integral of sine of x over cosine squared of x dx. And so this one, I don't see that up here in the table, right? Obviously it involves trig functions. I don't see any of these that involve trig functions. And I'm not going to be able to just, take the ratio, integrate the sine as one part, integrate the cosine squared as a second part, and just kind of smush them together, because the rules for taking derivatives are a lot more complicated than that. So certainly the rules for integrating are also going to be a lot more complicated than that. So this one's going to require actually a little bit of algebra. Just rearrange the terms. I could think of this as the integral of sine of x over cosine of x times 1 over cosine of x dx. And if I recognize sine over cosine as tangent of x, and 1 over cosine as secant of x, well, now I have something that does show up in the table right there. This integrates to secant of x plus c. So there's the result that we get for that particular one. Okay, so I want to move on to, real quickly, we're going to practice this, and what we're going to find is basically if stuff doesn't show up in this table, we're kind of SOL as far as coming up with integrals. We're going to need to learn a bunch of techniques that are sort of the reverse of a bunch of the derivative techniques that we've figured out. So things like chain rule, things like product rule. There are reverses of those rules that allow us to do integration. And most of those are going to come in Calculus 2. We'll start the first of those techniques in the next section in 5.5. But for now, this is pretty much what we're limited to being able to deal with, is stuff that shows up in this list. This is what we can integrate right now, and if it's not in this list, we don't yet have the techniques to handle that type of stuff. So, let me move on to the second part of the title of this section. Let me just go back up. Whoa. The Net Change Theorem. I want to talk about that for a minute. And so, let me sneak that in here. The Net Change Theorem. So we actually mentioned this in the last video, but we can actually reformulate the fundamental theorem of calculus into this thing that turns out to be called the net change theorem. So this is just a reformulation of the fundamental theorem of calculus, part 2, the second part. So what it says is that if you take the integral from a to b of our f prime of x dx, this is just f of b minus f of a. There we go. This is what the net change theorem says, that essentially the integral of some, whatever the rate of change is here, right, the integral of some derivative, and we've associated derivatives with rates of change, is just the net total change between the two ends. So we did this with the idea of velocity before. So this is a derivative, so this is some sort of rate of change. And if I integrate that rate of change, what we get over here is just what we call the net change, or the total change. Just figuring out how far apart is the original function at the beginning point and at the end point. So this is what it says. The integral of a rate of change gives what we call the net change, the total change. So, if you think about it in some sense, again, relating it to the idea of like a velocity, we could write the integral from, say, 0 to 100, where these are values of time. So I'm going to explicitly put t equals there so we remember these numbers represent time. And maybe we've got a velocity that I can write as the derivative of position. So x prime of t, this thing is a velocity. And I'm integrating it with respect to time, so dt. And all that's going to be is whatever the position is at time 100 minus the position at time 0. We kind of did an example like this yesterday. So if we keep track of the velocity at every instant in time and add up all these little distances we get from multiplying this velocity times this little bit of time, a tiny little bit of time, making this a little bit tiny bit of distance, and we're adding up all these little distances from t equals 0 all the way up to t equals 100, it's the same as just looking at what position were we at when we started, what position were we at when we finished, and take the difference. There's our net change. So this is, again, the total distance traveled from t equals 0 to t equals 100. Whatever these units happen to be, seconds, minutes, hours, whatever. So that's kind of the idea of our net change theorem, going back to the stuff that we talked about previously. Now there is a little bit of a distinction that I want to make clear. So I want to make clear that there's a difference between what we're going to call net change, which is our displacement, what we're looking at here, and the total distance that you've actually traveled. So let me make this distinction. Net change, which is what we've dealt with up here, versus the total distance traveled. Okay, so let me give you an example of something where we can see there's a distinction between these things, and I'll try to make it more clear what these things actually mean. So let's imagine this is my graph of time versus position. So my x of t. And maybe at our starting point here, we'll call it A, and it's going to be 0 in this case. We have a graph that looks something like this. Maybe it goes up a little bit, does this, comes down, and then we wind up right here. And right there is the value of b that we're interested in. So I want to look at a couple of things. What we've basically done, if we're keeping track of at various points in time, is we started traveling in the positive direction, right? Up is positive, down is going to be negative. So our position increased. We moved up from some initial height of 0 up to whatever this height is. So initially we started by going up. Then from this point we came back down. We kept going down all the way to here, then we came back up a little bit, and then we continued up. So splitting this all up into kind of sections here. We continued up to this point. At the end of the day, the net change is only this little distance. This is x of b minus x of a, because this height right here, oops, let me do it in a different color. This height right here, that's the ending position, and this height right here is the starting position. So in the end, that's as far as we wound up traveling, just that little distance. But the total distance traveled is really keeping track of all of these individual arrows, adding them all up, and then recognizing that at the end of the day, this piece canceled this piece, then this piece canceled this piece, and at the end, this was the only piece that really wound up mattering. In a sense, you could think about it as if you're, out running errands or something like that. You go all over the place. You drive out to the grocery store, and then you drive over to the hardware store, and then you go pick up your laundry or your dry cleaning or something, and then you wind up back home. And the net change in your position after all of that is 0. You wind up exactly back where you started. So your net change would be 0 because your starting position and your ending position are both at home. You started and ended in the same place. So your net change is 0, and yet your total distance traveled, if you look at your odometer on your car, is some number of miles. It just happened to all cancel out because we wound up back where we started. So this is the distinction between total distance traveled that keeps track of both increases and decreases in your position relative to your starting point, versus the net change, which just basically cancels all of these out and just looks at what is the difference between the position where you started and the position where you ended, if that makes some sense. Hopefully it kind of does. Get all of these out of there. Get all the red ones out of the way. There we go. So again, the net change is just basically the final position minus the initial position. So in this case, the final position is the x of b term. The initial position is the x of a term. And we just take the difference. Versus the total distance traveled, which is the sum of all those little arrows that we drew down there. So total distance traveled, this is equal to the sum of all of these arrows that look like this, all those little distances. So I guess I will do them in red, just make it totally clear. These are in red. Those correspond to these, keeping track of all of these little pieces, if that makes sense. So we sum all of those distances, right, ignoring the sign of each piece. So essentially, this distance right here and this distance right here, is if I just think of them as distances without a sign, maybe they're both 10 miles. I drove out 10 miles, then I drove back 10 miles. So I went a total of 20 miles. As far as my odometer is concerned, we drove 20 miles, even though they wound up canceling each other out, and I wound up back at the same initial displacement from where I started. I wound up back where I started. So the idea is, in this case, it ignores the sign when we're trying to find the total distance traveled. So let's see if we can do a more specific example here. So let me give you this velocity. Maybe our velocity v of t is this polynomial. So it's a function of time, and it looks like t squared minus 2t, whatever, minus 3. And it's the velocity of, I don't know, some particle. I want to find the total displacement and the total distance traveled. So in part A, find the total displacement. So the displacement or net change. So net change from t equals 0 to t equals 4. So between time 0 and time 4. So this one's easy. To find the total displacement, we just need to take the integral. It's the integral from 0 to 4, our starting time and our ending time. You can always add those little t's there, t equals, if you want to kind of just keep in mind what those variables represent. You don't have to. And we're just integrating v of t dt, because this is going to give us basically our total. So let me do it this way. Let me delete this and write totally clearly what I want. The idea is I'm looking for x of t, which is going to be the integral of v of t dt, right? That's position. And if we want, we can use integral from 0 to 4 using our net change theorem of v of t dt is going to be equal to x of 4 minus x of 0, in a sense. So that's the idea. X is the position, v is the velocity. When we integrate this velocity, we'll get position, and we're just going to wind up evaluating it between those two things. So let's figure out what that function is. What is the antiderivative, or in this case, again, I said we would drop that term. What is the integral of v of t? So in this case, this integral right here, integral of v of t is the integral of t squared minus 2t minus 3 dt, which is a 1/3 t cubed minus t squared minus 3t. And if we put in our 0 and our 4 here, we're just going to evaluate this between 0 and 4. So that's the idea. This is just, again, the integral by going term by term, using all the power rules. This became a t cubed, this became a t squared, this became a t, and I've accounted for the constants as necessary. And what do we wind up with in all of this? Well, when I plug in the upper bound, I'll get 1/3 times 4 cubed minus 4 squared minus 3 times 4. That is the upper bound. We're evaluating it at the 4. And then I will subtract off the lower bound, but you'll notice all of these involve a t, so when I plug in 0, every single one of those terms is going to go to 0. So I'm just going to write the whole thing as a 0. And what do we get out of this? Well, 4 cubed is 4 times 4 times 4. What is that? That's 64 thirds. We're subtracting 16 from that, and then subtracting 12 from that. And you can try to do this real quickly. If we do all of these in terms of how many thirds they are, get a common denominator here, I can rewrite that as, so we'll have 64 thirds. This is going to be 48 thirds, and 12 would be 36 thirds. So 64 minus 48 gives me 16. I'm subtracting off 36 from that. I think this is going to give me negative 20 thirds. And that is my net displacement, negative 20 thirds. I think I got that right, hopefully. If we find the total distance traveled, we need to keep track of when we were going which direction. And so there's a couple of ways we can do this, but the easiest way, in my opinion, is to start by drawing a picture. It'll give us some intuition for how we can treat this thing. So if I draw a quick picture of this, delete that, sorry. We are going to have something that looks like this. Again, this is t. So I want to put the velocity there. There we go. And I want to give a graph of what this velocity looks like. So remember, our velocity, I just wrote it up above, is, where did I have it? T squared minus 2t minus 3. To graph this, it might be easier to find the zeros first, so I might factor it. Let's see, t times something is something. So I'm looking for two numbers in this case that when I multiply them I get -3, and when I add them I get -2. So I think it's going to be a -3 and a +1. So -3, +1, and that gives me that the zeros of this thing, so are at t equals 3 and -1. And so if I draw those over here, 1, 2, 3, there's one of my zeros, the other one is over here at -1, so there's 3, there's -1, and this velocity is a parabola. It's a quadratic, so it's a parabola, and it has a positive t squared term, so it opens up. So it's going to look something like this. Something like this. I don't know exactly where that minimum is going to occur, but it's going to look something like this. So here is time 4, 1, 2, 3, and so on. Okay, so here's our picture of our parabola. This parabola represents the velocity. And what you'll see is that initially, up until this point, this line right here, in this entire region, so we're starting at t equals 0, and we're integrating. Here we go. I want to find the total distance traveled, and you'll notice that initially the velocity is negative. So from t equals 0, the velocity is down here somewhere. I don't know the actual value here, but it doesn't matter. I know that the velocity is negative starting at t equals 0 and all the way up until t equals 3, at which point the velocity becomes 0. So I'm going to travel in the negative direction for a while. And then from t equals 3 to 4, the velocity is now positive, and I'm going to travel in the positive direction. And I'll get some cancellation. What we did up here when we did our integral is we integrated and found this contribution, which was negative, plus this contribution, which was positive. So I had a positive contribution here in the red, a negative, sorry, in the positive contribution in the blue, negative contribution in the red, and when I added them together, we got this result. Right here was the positive contribution and some negative contributions, and the net result was this negative number. But what we're saying is if we're trying to find the total distance traveled, I don't care that I was going in a negative direction when I went this way and a positive direction when I went this way. I want to keep track of the total distance. So I want to find this integral separately, change the signs of all of them to positive. So the fact that this one's going to be negative, we'll ignore that, we'll flip its sign, and I want to add those two results together. And so it's important to know when we change directions when we're trying to find this total distance traveled. And that's why we want to find the zeros. When the velocity is 0, that's an indication that we're transitioning from a negative velocity, in this case, to a positive velocity. We're changing directions. You can think about it. If I am in my car driving, if I back out of my driveway, I'll start going in a negative direction, and then I'll hit the brakes and stop. My velocity will go to 0, and then I can drive forward to pull back into my driveway and wind up back where I started. And I, again, will have gone some distance, a negative distance initially, a positive distance out thereafter, and they'll cancel each other out. But to transition from negative to positive velocity or vice versa, we have to go through a zero. We have to go through a point where our car is stopped. So that's why it's important to find these zeros. In this case, the zero that we care about is the zero on the interval. Remember, our interval that we're interested in is from 0 to 4. The only one of these two that we care about is the 3, because this one is, the -1 is outside of the interval we care about. So what I want to do instead to find the total distance traveled is I'm going to do two separate integrals. I'm going to do the integral from 0 to 3 of t squared minus 2t minus 3 dt. And then when I get that result, I'm going to take the absolute value of it. And to that, I'm going to add the integral from 3 to 4 of t squared minus 2t minus 3 dt. And in this case, I won't need the absolute values because it's going to be the positive portion. But in general, just toss absolute values around to any of them. Any one of these integrals that winds up negative, just change the sign to positive and then add them all up. So this is going to be our total distance. And we've split it up into the negative region. That's this integral, and the positive integral is this piece. And we just want to sum the two together. Okay, so we've already found that integral. We did it up here. All right, we've got it right here. It's that same thing. We're just changing the bounds of integration now. So I'm going to have 1/3 t cubed minus t squared minus 3t evaluated from 0 to 3. And then I'm going to add to that, take the absolute value of that result, and add to it the same thing evaluated between 3 and 4. Okay, so that's what we'll get out of this. So when we plug in the 3's over here, I'm going to get 1/3 times 3 cubed minus 3 squared minus 3 times 3. From that, I'm going to subtract off a 0. So that, again, this piece corresponds to this piece. And then to that, I'm going to add the result. So I'm going to put absolute values around that. And then I'm going to add to that the result of doing the same thing over here, where incidentally, since we're plugging in this lower bound 3 here, and we already plugged in that upper bound 3 here, luckily we're going to be able to use this same number over here. So let me just do this one first, and then it'll save us a little time when we come back and do it a second time over here. So I still have to do the blue portion of this, and I'm going to give myself some room so we can actually see this thing. Okay, so for this first piece, I've got 3 cubed, but I'm also dividing by 3, so this is really just the same as 3 squared, and then I'm subtracting 3 squared. Those two pieces will cancel. This is 9, this is going to be -9, and then I'm subtracting 9 from that. The overall result of this is -9, but again, we're taking the absolute values. And so that is what this whole red piece simplifies to. And the blue piece now is going to be 1/3 4 cubed minus 4 squared minus 3 times 4. There we go. So that piece minus the same thing that we just wrote over here in red, the 1/3 3 cubed minus 3 squared minus 3 times 3 term, absolute value of that. So this comes from plugging in those two bounds. Here's the 4's, and here are the 3's. But again, we already found this number. We just did it. This whole piece winds up being a -9. And we did this piece earlier. That's what we did way up here, we already plugged in all the 4, so assuming I didn't screw this up, hopefully I didn't, that piece is negative 20 thirds. So I've got negative 20 thirds, and from that I'm subtracting a negative 9, and taking the absolute value of that. Whew. Okay, so from this first piece, taking the absolute value, is going to give me a 9. And this piece over here, I'm going to have a negative 20 thirds plus 9. So plus 27 thirds, if you want to think about it like that. So I can rewrite this as 9. That's this piece. And then this whole piece is going to be negative 20 thirds plus 27 thirds. That's those two pieces. And combining those two pieces together, I'll get my 9. The negative 20 thirds and the plus 27 thirds is 7 thirds, so I'm going to add 7 thirds to that. And if we again get our common denominator, this one's 27 thirds plus 7 thirds, for a grand total of 34 thirds is the total distance traveled. Good. I think we got that. So essentially what we did is we had a portion where we traveled in a negative direction. We had this other portion which gave us the 7 thirds where we traveled in a positive direction. And just to check, if I had kept the sign of this as being the negative sign, if I hadn't taken the absolute value up here, we would have gotten negative 9 plus 7 thirds out of this. And that negative 9 would be negative 27 thirds plus 7 thirds, which would give me the negative 20 thirds that we got way back up right there. So it looks like I didn't screw up the math, or if I did, I screwed it up very consistently. Again, this is just a side note. Don't really need this. It's just a quick sanity check to make sure I hadn't screwed something up silly. But the total displacement is we wound up negative 20 thirds relative to where we started, but the total distance we traveled was actually 34 thirds. We drove 27 thirds in the negative direction, then we drove back 7 more thirds in the positive direction to get to this negative 20 thirds. So here's the total distance traveled that includes both the negative direction and the positive direction, and here's the net displacement after taking both of those into account. So this is how you would compute net change versus total distance traveled. The difference is find the zeros. So net change is easy. That's a single integral. Total distance traveled is trickier. We've got to find zeros where we change direction and split our integral up into all of these pieces, some of which are negative, some of which are positive, and then take absolute values of each of those pieces because we don't care about the negatives. Driving south and driving north in your car both put miles on the odometer. Doesn't matter which direction we're going. So hopefully this makes some sense, and I will try to post the last video here shortly.